Hi everyone, welcome to my first video on video series on random and stochastic processes. In this video, I would like to talk about the definition and intuitive understanding of random processes. All right, so there are many definitions for random processes. The first one, for example, is that random process is a collection of random variables indexed by time. What do I mean by that? Assume the random process or a stochastic process s of t, right? Where t is changing from 0 to infinity, right? Um, so for example, here, like S1, S0 is going to be one random variable. S2 is S1 is going to be random variable. S2 is going to be another random variable, right? So it's a collection of random variable indexed by time. Now, one way to understand this definition is that to consider the random process as an infinite dimension random vector. So what was a random vector? Random vector was nothing but a collection of random variables. So for example, if we have x, as a random vector, it was x1 with the element x1, x2, all the way to xn, right? Which each xi is a random variable, right? So this is like a n-dimensional random vector. Now, random process, this n goes to infinity, right? It's an infinite dimensional random vector. You can think of it also like that. That's one definition. So let's take a look at this diagram that I have. So for example, if you fix t equal to t1, you get one random variable, s of t1. If you get t equal to t2, you get another random variable. So here I define it as well that random process is nothing but a collection of random variables. Now I need a bit of formality or definition. If this t is coming from continuous values, right? Then we call it a continuous time random process, right? So it depends on the domain. If the domain is continuous, we call it a continuous time random process. If this domain is coming from the countable set of integers, then it's called random sequence or discrete time random process, right? So if t is member of R, then it's gonna be any value is gonna be continuous random process if t is member of this natural numbers, right? So one, so for example, to be positive or not negative, then we get actually discrete time random process, or it's also known as a random sequence. But there is another definition for that. So there are two ways to look at the random process in a sense, right? Why is that? You see, this definition is not complete. Usually, random process defined or a domain of random process is two values, omega and also t, which omega is an element of sample space. And that's where the name random is coming from. The randomness is not due to time. All right, let's take a look at the second definition, right? So that's how usually you denote the random process, S of omega and t. But omega is element of sample space, right? In the probability theory, right? You have this sample space and you had a definition of random variable, which you map element of a sample space is a function, a random variable is a function, a mapping between element of a sample space to a real line, right? That was the definition of random variable. This is the same thing. So you have one omega. So for example, this is S of omega 1 and t. This is S of omega 2 and t, right? And this is S of omega n and t. So the sample space has n elements, omega 1, omega 2, and all the way to omega n, all right? So since we have two arguments, we can fix each argument separately and let the other one vary. So if you fix omega equal to omega 1, right? As I wrote here, if omega is equal to omega 1, then what do we get? We get one of these. We got one of these. We get either this one. If we get omega equal to omega 2, we get this one, right? We get S of omega 2t. If we let omega equal to omega n, omega equal to omega n, then we get this one, right? So if you let omega to be omega 1, for example, if you fix omega, you get a realization. You get a deterministic curve, right? So if you let omega equal to omega 1, you get this one. You get this time domain signal. You can also think of it like that. Time domain signal in electrical engineering usually is known as time domain signal, right? In mathematics, you call it the deterministic function of time. That's what you get, a time domain signal in a sense, right? If you let, so there is no randomness about this. If you fix omega, right, you get a time domain signal, deterministic realization as well. Now, what if you fix the time? If we go back to this definition that we have, if you fix the time equal to t equal to t1, let's see what will happen, right? If you fix t equal to t1, for the first one, you get this. For the second one, you get this one. For the nth one, you get this. So every time you get a different value, right? These values are not the same. You get a random variable. If you fix the time, you get a random variable, right? If you go ahead and fix them, t equal to t2, right? So you get this one. Next time you get this, right? Next time you get this one, right? So the very important take-home message is that the random process, the randomness is coming from element of sample space, right? Think of it like that. I want to give you an analogy, very important analogy. Remember it always like this. Consider random process is like a bag full of functions. Consider bag or box, right? This is a bag. Inside this one, we have full some functions. For example, some functions, right? Every time you close your eyes, every time you put your hand inside the bag and you grab one of this function, right? You don't know which function you grab, and that's where the randomness is coming from. That's for element of sample space. You don't know which omega you choose. That's where the randomness is coming from. Once you choose the omega, if I tell you that, hey, every time you put your hand in the box, you choose this function, then this is the deterministic function, right? If you know which function you're taking, it's a deterministic function of a time. So usually, in a sense, you will see in the literature that people omit this first variable, omega, and they denote the random process using S of t. And they assume that omega is already changing, otherwise it's not known as a random process. So that's why we usually write S of t, X of t, and we omit actually the omega, because we assume it's changing, right? So that's a nice definition I have here. If omega is fixed, the random process is just a deterministic function, realization. And if t is fixed, the random process is random variable, right? So note the randomness in random process is due to omega, not t. So it's due to an element of random, is element of sample space, okay? Next, we would like to talk about different classes of random processes, right? So by class, we talk about the continuous time and also discrete time. Now we talk about the more important class of random processes that are used extensively in different domains, especially in engineering domains, right? In signal processing, in machine learning, we use a lot actually, right? So